This is the first lecture of advanced graph theory. So in this course, we will assume all the concepts we have learned in the undergraduate graph theory course. In case you already forgot what we have learned in that course, I have uploaded the lecture note in the KLMS, so you can download it and then take a look at it. And please don't put the lecture note on the internet or publicly distribute. So there will be 3 elements in this course. There will be 2 lectures in each week. And there will be nearly weekly homework. There will be at least 10 homework. And then there will be study sessions, collaborative study session. There, you can come and discuss with other students. And you can discuss about homework problem or the lecture material, and it will be helpful. And the rough outline of the course is that we will deal with these 6 topics: network flow, matchings and factors, connectivity, coloring, planarity and minors, and extremal graph theory. I'm not quite sure, there will be enough time to cover all material, but I will try to cover those materials. So let's start the lecture. So first we will learn about network flow. So we all know what graphs are. Graphs are the mathematical object which consists of the vertices and edges. Usually we use it to model many networks. So here networks could be many things. It could be internet, or like the roads between the cities, or transportation network, or it could be many things. And in one particular situation is that assume we have some water pipe. And then the water pipes are linked each other. And sometimes more than one water pipe are linked. And each water pipe, water can flow into one direction. And then each water pipe, there is some limit on how much water can be flowing there. How much water per unit. So in some, you can say that each pipe has some capacity of water it allows to flow per unit time. Let's say in this pipe, you can, only flow 1 liter per second. And here you can flow 2 liters per second, and so on. And then there is some place, say source and sink. In this source, the water is provided. So water is going in here, and then through this pipe, water is flowing. And what we are curious about is how much water is flowing from this source to sink. It depends on how this water pipe network looks like. For some water pipe networks, you can flow lots of water, but some you cannot flow that much water. So let's make this concept more mathematical. So for that we define some terminology, and we define something called network. So network can have lots of meaning, but here we will define in this way. So network is a digraph, directed graph. So we all know what directed graphs are. It is a graph, and each edge is oriented into one direction. So a network is a directed graph, but it's more than that. It's equipped with a non-negative capacity for each edge. So this is exactly this, amount of the water that we can flow, the capacity of the pipe. And a fixed source vertex and a sink vertex. Say sink vertex is T, which represents the terminal, and source, we write it as S. You might wonder that why do we fix one source vertex and one sink vertex? Because there could be a situation that there is another source here, and then water is going this way, and then another sink here that we can consume the water here. But in those situations, you can actually reduce to this network, because we can simply add a super source and super sink. So this is S and T, and then you add these two edges, and then give the large capacity greater than the sum of all the other capacities in the original network. And then you consider this as a source, only source, and this as only sink. Then, and because these edges have large capacity, this network and the original network has the, same, are essentially same, in the sense that the amount of water that can flow from sources to sink in the original network is same as the amount of the water that flows from this super source to super sink. So here, this large capacity can be any large number bigger than the sum of the original capacities. In this case, we will just call it that we give infinite capacity. Here we say that the non-negative capacity is finite, but for our purpose, infinite capacity and then the very large capacity are, same. So we just say that we give infinite capacity means that we give very large capacity. Anyway, so this justifies that we only fix one source vertex and one sink vertex. Because if there are more than one, we can just add super source and super sink, and then add the edges with a large capacity between super source and sink, and then a super source to source, and then sinks to super sink. And this new network and then original network are flowing the same amount of water. It's not difficult to actually see why that's the case. And in here, we say a flow. F is this is a function representing how much waters are flowing. This is a non-negative real valued function on the edges of the network. So this is just non-negative real-valued function on edges. And it represents that how much waters are flowing in each pipe. Of course, I mean, here, this flow does not necessarily satisfy any constraint on this pipe. So flow itself could have situation that this flow is bigger than the capacity. But in that case, this is not good, non-feasible. So we will define the feasible flow in a minute, but flow itself can be any non-negative real-valued function on the edges of the network. And then we have to describe the good flow. What would be the good flow? Good flow should be satisfy some conditions. So one of the conditions is that if we have a disjunction and there is two water pipe, and then 1 liter is flowing into this junction, and 2 liter of water is flowing into this junction B through these two pipes, and then some water are flowing out. Let's say this is 3 liter and 4 liter are flowing out. Then this B, we are assuming this B is not source or not sink. If it is not source or not sink, then 1 plus 2 liter is the 3 liter of the water in total is flowing in, and 7 liter is flowing out. So which is absurd. Unless, somehow magically water is produced there, which only happens in source. You get 3 liter of the water and then you can flow out 7 liter is impossible. So we don't want this situation. And also, if there is a water pipe or the edge with capacity, say 5 liter, then obviously the amount of water that you flow here, which is F of E, you want this to be at most the capacity. Otherwise, you cannot flow 7 liters of water on the capacity, on the water pipe with capacity 5 liter. So let's, write these in mathematical language. For that, let's say for a set S, which is a vertex subset, we write F minus S for the total flow on entering edges, and S plus S for the total flow on exiting edges. So for example, if we have this S, let's say this is flowing 1, 2, 1, 2, 3. And then here it flow, let's say the other way, 1. In that case, from S, the edges that are entering S is this edge and this edge, entering from outside into S. So F minus S would be 3 plus 1 is 4. And F plus S is the exiting edge are only this one. So F plus S would be 2. Note that the edges inside here, inside S, contributes nothing to these two expressions. And also, let's say a vertex in a network is internal vertex. If it is in the network, but it's not source or sink. Then, what would be the give me a moment. Then what would be the condition that we want to satisfy for the flow is, so we say a flow is good or feasible is a flow that satisfies the capacity constraint. So the amount of water that flows from a water pipe should be between 0 and the capacity for each edge. So here this is the directed edge because we are on the network, which is a directed graph. And the conservation constraint, which means for one vertex, so for one vertex case, we write f prime, f plus v for a vertex is same as f plus the one vertex set v. So in that case, so you consider all the entering edge and exiting edge. And if this is 1, 2, 3, and this is a 2, then f plus v is you add all the capacity, all the flow value of the edges exiting. And for f minus, you add all the, values of the edges, which is entering V. Then, what we want is this conservation constraint is that for all internal vertices, the amount of water going in and amount of water going out are same. And for source and sink, by definition, we consider that the source is the somewhere that water is provided. You can consider it as a large reservoir of water or river or ocean. And then sink are where the water is consumed. So there, we don't need this conservation constraint. And we say the value and we write as VAL, value of F of a flow is the net flow, how much waters are produced from the source. So another, you can easily check that this is same as how much water are consumed at the sink. So for example, if we have this flow, so here, let's see, so this black, say this green numbers are the value of some flow, and then this black are the capacity of the edges. Then let's say this is source and this is sink. Then this is actually a feasible flow, because so for say this vertex, all the conservation constraint is satisfied. All the exiting edge, there are no exiting edge, only 3 entering edge, but those 3 entering edge has value 0, so 0 equals 0. Or the exiting one, entering one are same. And say for this one, 1 is flowing in from here, so 1 is flowing in, and total 1 is flowing out. So conservation constraint is satisfied there. And then here, 1, 2, 3. 3 flow amount of 3 flows are coming in, and then the coming out flow is also 3. So which is same. For here, you get 2 flows and then you distribute it to 1, 1. So the conservation law satisfied. And then all the green numbers are smaller than or equal to the capacity. And then all of them are non-negative. So this is feasible flow. And then what's the value of S? Value of this flow? You take this source vertex, and then it gets out the 1, 1, 2, 4. Note that which is same as the this sink. So again, this is 4 minus 0 is 4. So value of this flow is 4. And recall that we, in the undergraduate graph theory course, we defined the concept of cut for 2 vertex set, say S and T, and we write this S and T to indicate the all edges UV in the graph, and U is in S and V is in T. And for graph, this UV is undirected edges, but for directed graph, this UV could be the directed edges. So it depends on the context. So S and T, so for example, in graph case, so you have this E1 and E2, then ST is E1, E2. But directed graph case, we only take the E1 in this case. So what we are interested in is finding a flow with the largest value. Let's say the maximum flow problem is that of finding a feasible flow of maximum value. And to find the maximum value, we need to be able to check which values are maximum. For that, one of the useful concept is this cut. Not any cut, but the specific cut. So let's say given a vertex partition of the vertex set of the network into a source set. Source set is just a set containing the source S, and a sink set T. Again, sink set is a vertex set containing the sink S. We define the capacity of the source sink cut. Let's say this cut of S and T is the collection of all directed edges from S to T. And then if S contains the sink and T contains the, S contains the source and T contains the sink, then we say this is the source sink cut. And we define the capacity, which we write as cap capacity of S and T is the total of capacities on the edges of this cut. So we consider about this capacity of the cut, because that's quite useful in a sense that it provides some upper bound on the value of flow. So for example, if we have some cut S to N T, and then the capacity is 1 liter, say here 1 and here 1. No, let's say 2 and here 3 is the capacity. In here, we have S and T. Then no matter how we take the flow, the maximum amount of water that can flow from S to T is bounded by the capacity of the cap, because water is producing here and then it's flowing, and then here it flows by at most 1 and here it flows by at most 2, and then here the best case is no flow is going from here to here. Then the maximum water that can arrive to T is at most 3. So later we will see that this will provide a good upper bound for the value of flow. So that's why we define them. So now our interest is that we want to find the maximum maximum flow. For given network, we want to find the maximum flow, and then we want to find it in some efficient way. Then we need some tool. Before talking about the tool, let's first, we need to actually prove that there exists some maximum. If we want to find the maximum flow, then we have to first prove that there exists a maximum flow. So it's possible to actually talk about maximum flow. Say Lemma 1.4. In every network, there always exists maximum flow. So it makes sense to talk about this maximum flow. And the proof is Actually, not difficult. Let M be the number of edges in there. And then, what is this flow? Flow is nothing but a function from the edge set to real number. More specifically, non-negative real number. So flow is a point in m-dimensional space, Rm. And feasible flows are, in there, feasible flows form a compact set. Why is that? Feasible flows are the flows which satisfy the two conditions. One is that capacity constraint, and then the other one is conservation constraint. Capacity constraints are the ones that, you have to have this inequality. So in other words, you take the one coordinate. So let's say you have the flow is same as the flow with E. And here you take one coordinate and then you restrict the coordinate between 0 and some number. This is a closed set. So once you take a closed set in this Rm, and this is for all E. So you get a bounded closed set which is compact. And then further, you have to satisfy some linear equality, which is summation of this Fe for certain, E is same as summation of all the edges which, leaves B and entering B. So in terms of Rn, so these are the summation of certain coordinate, and these are the summation of certain coordinate. So this is a linear equation. So for each internal vertex, you add a linear equation. And once you have this compact set, and then you add linear equation to the constraint, then you get a smaller set which satisfies the equation. But once you shrink this way, it's still compact. So we know by the elementary analysis, this is compact. And also this value of f is a continuous function. It's more than that, it's linear function, because this is simply the summation of all edges exiting from the source minus summation of all edges entering to S. Maybe this way of writing was not rigorous. Let's write U, U. So V, U. Yeah. So this n plus n minus is out neighbor. So U, So SU and US. So each of these are the coordinates in this Rm. So it's the sum of the several variables. So it's a linear function which is continuous. And we know that any continuous function on a compact set has a maximum value in here. So hence it attains its maximum on the set. So this shows that there exists maximum flow. Yeah, this is one network that I'm using as an example, but it seems that I'm keep postponing to actually use it. So we know that maximum value exists. And then, as I mentioned before, the capacity of a cut provides an upper bound. The value of max flow. So which is captured in this lemma 1.5. So if F is any feasible flow in a network G, and oftentimes if we say flow, let's just assume it is feasible flow. So from now on, we don't consider any non-feasible flow. And we have this source sink cut, ST, between two vertex set is any source sink cut. Then we have this upper bound on the value of this feasible flow as the capacity of this cut. The proof is not difficult. Essentially what we want to show is that the value is we have S here and T here. Then the amount of water that flow out here. And then there are some of the water are flowing inside here and then even going this way or this way. But the amount that's flowing here, it stays inside of this S. So there has to be, because of the conservation law, there has to be some flow. If this flow has certain value, then that much water has to flow out from this S to go to T, and which can be upper bounded this capacity of S and T. So let's write it in more rigorous way. The value of S is the amount of flow coming out of S minus flow going in S. And then for all internal vertices in S, we take this number. No, okay. So let's write it this way. So value is this. And once we add 0, it doesn't change anything. And then this 0 is actually same as adding this. Because of the conservation law, for each u, this number is 0. So we add 0 many times, so this entire thing is 0. So value is same as this. But this one term and this term, and this one term and this term can be collected. So this is actually the summation of all vertices in F. You sum the F plus and F minus, and you subtract it. And you then this is same as the F plus S minus F minus S. And what's the F plus S? It's the edges from S to outside. So this is same as summation of all value U in its S, P is not in S. So P is in S complement, which is same as T. And UB is the edge of G. Because T is the complement of S, because the source sink cut is defined as the cut formed by S and its complement. So S and T are the partition of the vertex at G. So this is same as this. And then this term is non-negative. So you subtract 0, then it's upper bound. And then because of the capacity constraint, this is summation of capacity of UB, and which is same as, over all the same summation, and this is same as capacity of S and T. So this shows that we have this inequality. So this shows that if you want to prove that a given flow F is maximum, then it's suffice to find the cut, source sink cut, with the capacity equal to the value of F. So if you want to prove that F is a maximum flow, then what do we have to do? We have to show that this is a feasible flow, which is okay. But we want to show that this value is maximum possible. Maximum possible means that any value rather than this is impossible. So we want to prove some upper bound on the possible value. So the way is that find a cut. So source sink cut. With the value of F is at most capacity of Ts. Then we prove that F is indeed a maximum flow. So this is a useful strategy. And to prove that F is maximum, this is one good strategy. And what if we want to prove that some F is not maximum? To prove that F is not maximum, then what should we do? So we want to find the maximum flow, so we want two tools. One tool that can detect a maximum flow. So once a flow is given, We want to check whether, if that is maximum. And also we should be able to check whether this is not maximum. If this is not maximum flow, then we cannot find the source sink code with the same capacity. But we cannot, we cannot be sure that, it is, maximum flow or not yet. Just the fact that we cannot find the source sink code with the same capacity does not necessarily mean that it is not a maximum flow yet. So we need some tool to prove that some f is not maximum. How do you prove something is not maximum? Then the most easy way is that we just find a better one. If we find a better flow, then it automatically gives that this f is not maximum because we just found the better one. Then how do we find the better one? So one of the way is that for given flow, we can adjust it to produce a better flow with a larger value. And how do we do it? We can do it in some somewhat local way. So how do we do it in this specific case is that we take, say, these passes. So in this path, let's direct the passes in this way. Note that this particular edge, we directed this red one in the opposite direction, but let's not worry about it for now. And then what we do is, okay, now I see that I have put some wrong number here. Sorry, let's just say this was 2, 2. Assume this was 2. Then what we do is we can change the value on these 3 edges so that this is now 1 plus 1 and this is now 1 minus 1. This is now 1 plus 1. So this is 2, this is 0, this is 2. Then what happened? You can see that the conservation law still holds on these 2 vertices and everything else is still okay. And then capacity constraint is still okay because this 2 is at most 2, 0 is between 0 and 2, and 2 is still between 0 and 3. And then here, the value, this value used to be 4, but this value is 5. So it increased. So this shows that we can do better. We can find a better flow. In order to do this, we found this path. And what was the property of this path? On the way, these 2 vertices were not full, meaning that this 1 and 1 was strictly smaller than the capacity. And another property is that this opposite edge, this is an edge which is oriented opposite way than this red path, which has strictly positive. So those are the essential reason why we could do this. Here we add 1, but we don't really have to add 1 per se. We can actually add any epsilon and we can subtract any epsilon as long as it makes sense. In order to add and subtract this epsilon, the condition that is necessary is that this value is smaller than 2, the capacity, this value is smaller than 3, the capacity, and this value is strictly positive. So, to make this more formal or mathematical, let's define such concept. So let F be a flow in a network G. Again, when we say flow, we only consider feasible flow. And we say a path P, which starts from U0 and then ends with UK in this G, is an F augmenting path. Say from UK. Wait, did I write it correctly that it is from? Give me a moment. Let's say for now, let's say 2. If it satisfies the condition that I described on the top. So what's the condition? It should start from the source. And all the edge, directed edge, here, this is smaller than the capacity if, say, let's just write it here. UI plus 1 is oriented in the correct way, and if it is oriented in the other way, in this directed graph, the network G, then it must be positive. And then, in addition, if UK is the terminal vertex, the sink vertex, then we simply call P on F augmenting path. So this defines the previous concept. So this path was F augmenting path. That's the reason why we could augment this flow into a flow with a larger value. So what's obvious here is that if an F flow exists, F augmenting path exists, then F is not maximum. But not only that, it has a better property. The converse also holds. So we can show that a flow f is maximum if and only if there are no f augmenting passes. So this can shift, our problem of finding maximum flow into finding f augmenting path. If we want to just find the maximum flow, we might have to check all the possible flows and then compute the values, and then you can choose the maximum flow. But checking all possible flow is too much. But here, f augmenting path is something more concrete, which is more concrete to actually check. So this is a useful lemma for us. So how do we prove this? So this direction is easy. A flow is maximum, then there are no f augmenting paths. Because if there is an f augmenting path, then we can augment it. So let's not just write easy and let's prove it. So that for given this flow, let SF be the set of vertices such that S is there and all vertices U such that there exists on f augmenting path. To U. So which is well defined. So for example, in this case, we have this S, and then this vertex is in SF because, this edge is not full, so you can directly add it. So this is an F augmenting path from S to this vertex, and then this as well. But this is not, because this is not F augmenting path, so we cannot add it. And this is also not, because this is not F augmenting path, we cannot add it. So from here, this is 0, so this we cannot add it. This is not, this two, edge path is not an F augmenting path, so we cannot add it. And by the same logic, this is not two F augmenting path. From here, we can actually add this. So this is F augmenting path, and this is F augmenting path. And again, this is F augmenting path. So SF actually contains every vertex here. So that's the definition of SF. And if terminal vertex is in SF, then there exists an F augmenting path P. And what we do is we let epsilon of P to be the minimum out of all numbers CUB minus FUB for all edges which is correctly oriented in the path, and all numbers FUV for the edges which is in path, but the sorry, this must be VU. In the graph G, so which is oppositely oriented than the network. Then we know that the terminal vertex is in here, and epsilon of P is positive. So there exists a F augmenting path from no, sorry. Let's not write it this. Since P is on F augmenting path, we know that this is all positive and this is all positive. So these two numbers are all positive. And then there are finitely many positive numbers. And then epsilon is the minimum, so we know that this epsilon P is positive. So we consider the flow F prime obtained by increasing F by epsilon P along all edges of P directed away from S, and decreasing F by epsilon P on all edges of P which is directed towards S. Here directed away and directed toward means that in the original network it is directly towards S or away from S. Then F is not maximum because we just obtain a better F prime. It is easy to check that the F prime has value larger than F. So value of F prime is actually value of F plus epsilon P. And the other direction, suppose T is not in SF. So there is no F augmenting path towards the sink vertex. Then what happened? We take the S, F, and its complement. This is a source sink cut in the network G. And you have this SF, and you have this complement. Then, what does it mean? If there is some HE between these two, from SF to its complement, then what it means is that there is this path from S to here, which is F augmenting path to this U. But if we extend it by adding this E, then this is no longer F augmenting. It was F augmenting before, but now it is not. That means f of E is C of E. It's already full. And for the edges which is oriented from the complement of SF to SF, again by the same logic, we have this F augmenting path, but once we add this is no longer F augmenting path. That means F prime of E prime, F of E prime is 0. So what do we have? The value of F is simply same as the F prime S minus F minus S is F plus of SF minus F minus SF. So this is the value of flow, because in this summation, every edge inside of S is, added once in this term and the other once in this term, so they canceled out. And so we can show that these two are the same. This is simply same as the capacity of this cut, because which is exactly summation of all the edges in SF to its complement and F of this E, and then we just show that this is same as the capacity, and then so this is same as this plus this minus. Let me write it in 2 steps to make it more clear. So because all the edges inside of S are cancelled in this term, this is actually same as the, adding all F. E is from the SF to its complement, and this E is from its complement to SF. And this is same as summation of all capacity minus summation of 0 by the definition of SF, by this observation. And this is same as capacity of SF and its complement. Hence what we have? Hence we have the value of F is same as capacity over some source sink cut. That means there is no other flow, feasible flow with a larger value. So F is our maximum flow by the previous lemma. What was the lemma? 1.5. So we have this characterization of maximum flow by something more concrete, which is the F augmenting path. So from using this, what we want to show is this theorem, which is called max flow mean cut theorem. So in a network, the maximum value of a flow equals the minimum capacity of source sink cut. So I know I'm a bit over time, but let me just finish this proof of this theorem, and then we will be done for the first lecture. And because this is quite simple, so theorem 1.8 say, we know that there exists a maximum flow. That's one of the theorem that we proved before, which is 1.4. By lemma 1.4, a flow with the maximum value exists. Let it be f. And let gamma be the minimum capacity of among all source sink cut. Then we know that f is maximum, so there is no f augmenting path. So by the above definition, this definition, we use it again. We can consider this set SF. Then in the proof of the previous lemma, we just show that the T is not in SF. So SF and its complement from the source sink cut. And for this, we know that the capacity of this cut is same as the value of F, which is what we just show in the proof. So this proof. So we use this to show this equality. And then by the definition, what's gamma is the minimum among all capacity of source sink cut. And this is source sink cut, so this is M most gamma. But we already know that the value of F is M most gamma because of the lemma 1.5. So the theorem is proved. So today we defined what networks is and what flows are. So we define network, which is a mathematical model which models the situation that there are like flows from some source to sink, and then we want to find the sink with the maximum, flow with the maximum value, which means, flow that transports maximum amount of water. And for those flow, we want these certain conditions to be satisfied. Then we define this cut, and then we show that maximum flow actually exists. And then this capacity of the cut plays the upper bound of the value of the flow. And then we define this F augmenting path, which is a convenient tool to analyze whether a given flow is maximum or not. And it actually characterizes the maximum flow as the absence of the F augmenting path is equivalent to the statement that the flow is maximum. And then it shows that this max flow mean cut theorem. In a network, the maximum value of a flow actually equals the minimum capacity of a source sink cut. So instead of finding maximum value of a flow, you can simply compute the minimum capacity of source sink cut, or the other way, vice versa. Whenever you want to know one, you can actually find the other. So next time we will learn about some algorithms to find the maximum flow. And also lots of time flows with the values integer is important. So we will learn some theorem about integral flows, so which means that the integer with the value, flow with the integer values. So that's what we will do next time. Yeah, thank you for listening to this lecture.